Coastline. So,
So I'm trying to share the presentation, but I think maybe can I send to you the
yeah. While we are doing that, I think let me do a brief introduction
okay.
to today's activity. So, ladies and gentlemen, I welcome you once again to this program, and in particular, I welcome you to day 2 of the FAST4Future Summer School on Space Technology and Application. We had our opening event yesterday, and this morning we are going into the main thing. And today we are going to listen to some of our experts that will be talking to us on satellite communication. And today the lead instructor will be Dr. Ali Krenz Kiadutje. Sorry if I didn't get the name correctly. Maybe in the course of presentation, then let us get your name in better form. So Dr. Ali Krenz has a PhD in physics, specializing in ionospheric studies from the University of KwaZulu-Natal in South Africa. And he has held several teaching positions at different higher educational institutions in South Africa. And currently, Dr. Ali Krenz is a postdoctoral research fellow at the South African National Space Agency, SANSA. So I think we couldn't have chosen a better instructor for this very topic than you. And you will dictate the pace and tone of this lecture. Of course, as you have the program, the lecture will be for barely about 2 hours, but there will be a break in between two segments of the lecture. So, Dr. Likens, it's over to you now to give us your lecture on satellite communication.
Okay, thank you.
Thank you.
So I don't know if I have sent the presentation to Odo. I'm trying to share, but I don't see the presentation on my screen. Maybe let me try and see if you can see my presentation.
Okay.
Okay. Do you see anything?
Yeah, yeah, I can see something.
Okay. Is it a presentation?
It's not in the presentation mode.
Because yeah, it is too small. Um, Maybe I can log out and log in again. Or you can, is it possible to share from your side, to share the slide?
It may be, but let me consult my ICT expert to see
I
how.
have sent to Odo the
You have sent to
presentation.
me.
Yes.
Okay, let me check the email and see whether I can download it.
Okay.
He says he has sent to my email. Okay, so it needs to doing. Okay. So, going to sign it. Fail on your phone. So you don't already sign it.
So when I try to share, I see that they are taking
Okay,
me
so
to
you can sign
use
it.
system desktop capture. Sorry, sorry, Odo. Let me know if the presentation is ready.
Okay, just hold on a little. We are coming on.
Okay.
Good.
Okay, yes, that is the presentation.
Good. I think we are good to go now.
Yes, now you can put in the presentation mode.
Okay. Let's take that in out first. We did this first one. That's it. But you have to change slide now. Only once. So, it's full screen. Good. I think that's okay.
Yes, thank you. So my name is Ariklian Sehedu Tuje. I'm a researcher at the South African National Space Agency. I work on the ionospheric study using the HF instrument. So today I'm going to talk about the communication and the satellite technology during this online summer school, which is on the space technology and application. So as they have told you, my background is physics. I did a little bit of astrophysics and astronomy during my honors. And also I did my space physics during my master's and the PhD. So without delaying, we can go to the next slide. Is it okay if I can switch off my camera?
Yeah, it's okay.
Okay, thank you so much. Okay, so in this presentation, we are going to talk about the introduction to communication. I'm going to touch on Newton's and the Kepler's laws of motion. We are going to discuss about geo and non-geostationary orbits, satellite components, spacecraft subsystems, telemetry tracking and command subsystem. We are going to see that artificial intelligence are also used in satellite operations. I'm going to give you some basics on how the space weather can affect the satellites in general. And at the end, I'm going to give you some application of satellites when the satellite is already in its orbit. Next slide, please. What is communication? So communication is the process through which people exchange their ideas, information, feelings, or thoughts with one another. So this exchange or communication can be thought through speech, body language, gesture, eye contact, or symbols. So this word came from the Latin word which is communis, meaning common. So once you have a common thing with another person, that means you can communicate. Or if you need something from someone, you can communicate. So on this image on your right side, it is showing that it's another definition of communication where they're saying that communication is the act of giving, receiving, and sharing information through verbal and non-verbal method. So that is, I think, a simple and easy definition of communication. So a good communicator listen carefully, speak or write clearly, and respect different opinions. So that is a good communicator. In our daily life, communication helps us build relationship by allowing us to share our experience and needs and help us to connect with others. Next slide, please. So this is a diagram showing how communication is done in a simple way. So first of all, if you want to communicate, you must have an idea or a message. So that message, you must send it. If you send that method, depending on the method you use, it can be encoded, or you can use something which cannot be uh, interpreted by anybody. Then you use what we call communication channel, and that then the message is decoded, which means it can be it can be translated to the language the receiver can understand, and then the receiver can also give you feedback. So when I was kid, my father used to send me an envelope to his friend. So he used to give me an envelope of money to send to his friend, but I didn't know what was inside the envelope. So I will take the envelope and go to that home where that friend was staying, and then I give him the envelope. So when I give him the envelope, the friend also used to tell me, go and tell your father, thank you. That is the process. So my father had to communicate and then has an idea or a message. That message, I was I would say that I was maybe a channel. So I was being used to transmit the message, and then I had to bring the feedback. The feedback which was thank you from the other person. So that was it's an example of a communication. Next, please. So you need four skills in order to communicate. Number one, you need to listen, you need to speak, read, and write. So those are the basics anyone from your childhood have been going through. They train you to listen, to read, to speak, and write. So you must, of course, have good eyes. You must have good ears. You must also, your mouth must be working properly, and you must have tools to use like electronics, microphone, and others. So when you want to write, you must have your pen and papers. Also, sometimes you need the computers and tablets to write your message. So those are the skills which you need to communicate uh, perfectly. So please, can you go to the next slide, please? Now, these are examples of way of communication. If you want to communicate, long time ago, they use, even now, they're still using landline telephone. You can use the FM and AM radio. You can use a computer. Now we have a Wi-Fi. You have also social media, mobile phones, fiber optics cables, and the emails. So those are examples of communication, the way you can use to communicate. The figure on your right shows the devices which are used in the security companies when they are communicating. Most of them, they use the HF instrument. Next, please. Thank you. So communication, it can be done using two options. You have wired communication or wireless communication. So in wired communication, you need, of course, wires, which is also, it is called the line communication. So this one is divided into four parts, which is parallel wire communication, twisted wire communication, coaxial cable communication, and optical fiber communication. So you can see that for wires, you need, of course, from the sender to the receiver, there must be a wire connecting the two so that the information can go through the wires. So can you go to the next slide, please? Thank you. So now the second way of communication, which is our interest, which is the interest of for this topic today, is space communication or wireless communication. So for wireless communication, you don't need any wire connecting the two people, the sender and the receiver. So you only need the devices which are able to transmit electromagnetic signals. So this communication is called space communication, where it is done using the waves can travel close to the ground, which are called the ground wave communication. They can also travel at around 90 to 400 kilometers above the surface of the Earth, which is your sky wave communication. Also, they can use very far away, like 30,000 kilometers away from the ground, which is most of the case in satellites. So those are called space wave communication. So an example here, we give a satellite communication, and that is where we're going to focus our time during this topic. So the figure on your right, sorry, go back, please. So the figure shows the most of technologies which are used in communication. You have a towers, you have a router, you have a Wi-Fi, you have a camera, you have the computers, you have a mobile, you have a antenna, you have a drones and satellite. So all of those ones, they are used in wireless communication. Can you go to the next slide, please? Thank you. Now, in wireless communication, they use electromagnetic waves. You already know that electromagnetic waves, you have long wave and short wavelength wave. So for radio communication, they focus on long wavelength, which are, of course, which you can see on your on this image on your left-hand side. It is showing that radio waves, they have a wavelength of more than 100,000 kilometer up to 1 millimeter. So that range is where our radio broadcast, mobile communication, navigation, remote sensing radar, and the other technological devices are operated in. So other wavelengths which are not important for this topic, you can see them on the figure on your right-hand side, which can go to the application in the X-rays when they take the images in medicine. You can also see ultraviolet, but those ones are not very important in our discussion. So for this moment, our topic focuses on the long wavelength waves, which are a part of electromagnetic waves. Next slide, please. So those waves, they are divided into extreme low frequency. So I'm not going to read the numbers, but the values, you can see the middle column has the ranges. The wavelength, I'm not going to read them, but I'm going to only state their applications. So those ones are used in submarine communication and geophysics. Now you have a super low frequency, which are used in mine and cave communication. So you have ultra low, which are used in seismology, secure military. You have a very low frequency, which are used in navigation and time signals. Raw are used in AM raw wave and RFID. Medium frequency are used in AM broadcasts and maritime. High frequency, this is where that is where I'm focusing myself currently in my research. So we use frequency between 3 and 30 megahertz instrument, and these are used for short wave, citizen band, but also we use also them for in research and other things. So very high frequency are used in FM, TV, marine, and air band. Ultra high frequency are used in digital TV, mobile, and GPS. Super high frequency are used in radar, Wi-Fi, and the SATCOM. Extremely high frequency are used in 5G and radio astronomy. Okay. Can you go to the next slide, please? So wireless communication without satellite. So not all wireless communication are done with using satellite. Some they are not using satellite. For example, mobile phone are connected to cell towers. Wi-Fi is connected to a router or access point. Bluetooth uses short-range radio waves. Radio and TV broadcasting, FM, AM, digital TV are connected on ground transmitters. Walkie-talkie two-way radios are connected to antenna. Radar systems send and receive signals from a targeted object. HF, VHF, UHF radio, including ionospheric reflection for long range. Microwave links are connected between towers. Next slide, please. Microwave component. Microwave components are electronic components that process electromagnetic signals in the microwave frequency range. This range is between 300 megahertz and 300 gigahertz, and their wavelength are between 1 millimeter and 1 meter. So that is a specific range which is operated in those wavelengths. So microwave components are divided into two parts. We have the active and passive components. Let us start with active components. Active components are those that need an external power source to drive them. They are used in amplifying, mixing, generating signals. So examples you have here is you have amplifiers and mixers. Now, passive components do not require external power source and are used in conduct, select, isolate, and transmit signals to maintain signal quality and path control. So the examples of those ones are filters, isolators, and antenna. Next slide, please. So microwave components are the key to the smooth operation of wireless communication. So they are used in wireless communication, in radar systems, satellite technology, medical equipment, military radar, and other smart devices. Microwave components are very important because they are used in technology that enables high speed, stable, and accurate signal transmission. Microwave components such as oscillators and the filters control and stabilize the operating frequency to enhance reliability. Lower noise amplifiers or high selected filters enhance the signal, reduce noise, and preserve the original wave from interference and distortion. So that is the importance of microwave component. Thank you. So the power amplifier and transmission line structures play a role in saving energy during the transfer process, source to receiver. Isolators and direction couples suppress reflect waves and external interference to maintain unidirectional and stable signals. Microwave component ensures that every piece of information from communication and navigation to medical and defense system is transmitted accurately, quite quickly, and safely. So those are some of the devices of microwave component electronics. Next slide, please. So the application of those microwave technology, you have what we call L-band between 1 and 2 gigahertz. They are used in mobile communication, GPS, and some radar applications. S-band from 2 to 4 gigahertz, weather radar, selected military communication, and satellite communication. C-band between 4 and 8 gigahertz. They are used in television broadcasts and telecommunication. X-band, which is between 8 and 12 gigahertz, is used in military radar systems and some satellite communication. Ku band, which is 12 to 18 gigahertz, live satellite services, and high resolution radar systems. K-band, which is between 18 to 26.5 gigahertz. It is used in high bandwidth satellite communication and some radar application. Ka band between 26.5 and 40 gigahertz. It is used in high-speed internet service and satellite communication. Q band 30 to 50 gigahertz, specialized in satellite communication and high bandwidth data transmission. U band from 40 to 60 gigahertz. It is used in scientific research and experimental communication technologies. V band from 50 to 75 gigahertz, millimeter wave communication and automotive collision avoidance radar systems. E band, which is 60 to 90 gigahertz, it is used in higher speed wireless communication and the millimeter wave application. W band 75 to 110 gigahertz, millimeter wave imaging and the high bandwidth communication. F band, which is from 90 to 140 gigahertz, it is used in deep space communication and scientific experiments. Lastly, the D band, which is from 110 to 170 gigahertz, is used in advanced scientific studies, which is physics and astronomy. Next slide, please. So now we are going to see, we are going to see the laws, the Newton's law and the Kepler's laws, because they are used in satellite launching, and they are applied when the satellite is already in its orbit. So we start with Newton's laws of motion. If you did physics at high school, I'm sure you remember those laws. So the first law states that an object at rest will remain at rest unless an external force is applied on it. So if you don't apply any force on any given object, that object is supposed to remain in its position of rest. Or if it was in a uniform rectilinear motion, it continues its motion until that external force is applied on it. So that is the first law of Newton. So I try to put this in a formula in a mathematical way, which I say that the resultant force or external force on any given object must be equal to zero. That is the short way of saying the first Newton's laws of motion. Because if it is not zero, then that object has to follow the second law of Newton. So the examples here, those are, you see the ball there, which is at rest. So if there is no force on it, it will stay there forever. And the next image shows two people pushing each other. If we assume that the two people have equal forces and they are pushing in opposite direction, the object will not move because the resultant force is zero. And the last image shows that the person is pushing to the right, which means that object, because it is being pushed, it has to go to the right in the same direction as the applied force. So that is law number one. Next slide. So Newton's second law of motion states that whenever you apply a force on an object, that object, it has to accelerate. And the acceleration, it must be in the same direction as the applied force or the resultant force, in short. So in a mathematical way, the external force, the sums of all external force, the resultant must be equal to the mass of that object times its acceleration, which means if you want something to move, if it was at rest, you have to apply force. If the resultant force is different from zero, then the object has to accelerate. So this, then you can see the image on your right-hand side, which shows that if the object has a force, there is a force applied on it, which they are using a vehicle that carries the satellite. So that object, it has to accelerate in the direction of force. And that is the second law of Newton. Next slide, please. So this is Newton's third law of motion, which is about action and reaction. So Newton discovered that as long as you apply a force, which we call applied force is called the action, of course, there must be an equal and opposite reaction to the applied force. And actually, this is very important in the satellite launch, because when they're launching satellite, you can see your image on the right-hand side, they usually use fuel. So the fuel, they produce this okay, in short, I can say they produce the action force, which is pointing toward the ground. That, because the ground has to react according to Newton's law of motion, then it has to push forward the rocket. And that force is the one which is actually used to launch the rocket. So it's the reaction force that accelerates the rocket into the space. Next slide, please. So that's what I was giving as an example for rocket engine thrust. So the engine, they all act to produce the action force, and then there is a reaction, then you get your object to move
Okay.
because of the third Newton's laws of motion. But we all use the third Newton's laws of motion when you're walking. So when you are walking, you have to use friction. So when you apply the force on the ground, if there is no friction, you can't move. You will slipper. But if there is a friction and you apply force, the ground is going to push you forward. That is how we are able to move. Even the tires of the car, everything, most of things, they move because of Newton's third laws of motion. Next slide, please. Okay, now we assume that your satellite was sent to the orbit. So now we are going to see Kepler's laws of motion, because Kepler's stated also three laws of motion, which are important, that those laws, they govern object in space, especially when one object is surrounding the other one. So satellites orbit the Earth and the Sun, obey the same laws that govern planets' motion around the Sun. We all know this for Kepler's laws of motion. So, sorry. Kepler's law apply when two object bodies in space interact by means of gravitational force. So this is the gravitational force now. So, when you have a two object, because of gravitational force, the two objects must have a force between each other. So depending the force, it depends on their mass, the product of their masses, and also it depends on the inversely proportion to the distance between them. So that distance square, its inverse, it depends on. So that means if those objects stay far away from each other, the force is going to be very small. But if the objects are very close each other, because of the inverse proportionality, the force is going to be very big. The interaction force, which is here in this case we call it gravitational force. So these are the images showing that the object rotating around the sun. I think this is the around the sun, and the other one is showing how satellite, they rotate around the Earth. Next slide, please. Okay, so this is now the first law of Kepler. So the first law, of course, it says that whenever an object is rotating around the sun, let us say the sun or the Earth will be at one of the two focus of the elliptical path. So the ellipse in the mathematics, the ellipse has always two focus, which is F1 and F2. So when the object is rotating then around the Earth or around the sun, always there will be that the motion has to be in a way that the Earth or the Sun has to be at one of the focus of that elliptical path. So that is the law number one. So it is written here, the path taken by a satellite around the Sun is an ellipse. Of course, it's an ellipse where the Sun or the Earth has to be at one of the focus, either at F1 or F2. Next slide. All right, so for ellipse, you have to discuss about what we call semi-major axis. This is the longest distance in those axes, the two axes, because it has two axes, semi-major axis, which is A in this case, and the semi-minor axis, which is B. So the eccentricity, if you calculate the eccentricity, which is given by the square root of A square minus B square over A, this parameter helps us to define, to know different shapes of our path, the path taken by a satellite or any other object rotating around the Sun or around the Earth. So the center of mass of the two-body system is known as the barycenter and is the center of the two forces. When the eccentricity is between 0 and 1, this is where you have ellipse. This is called ellipse, which means A is always greater than B. A is bigger than B. So when E is 0, eccentricity is 0, it means that A and B, they are equal. So when A and B, they are equal, we have a circle. That is a circular motion. So that is a specific case of ellipse. And when E is equal to 1, you have a parabola. When E is greater to 1, you will have a hyperbola. Those who did mathematics, they understand. Okay, thank you. Now, for the second law of motion of Kepler, he stated that a satellite will sweep out equal area in its orbital plane, focused at the barycenter for equal time intervals. So if you look at your figure on the right-hand side, so we have two areas, area number 1 and area number 2. So those areas, according to Kepler, they must be equal if that object is rotating around the Sun. So they must be equal, but after obeying only one condition. If the time taken to travel distance 1 is equal to time taken to travel distance 2. That time, if the time is equal, then the areas must also be equal. So the origin of the area, note that they are from the center of the Sun. So the only thing which will be different is going to be the velocities. Because you know that when you calculate the velocity, velocity is the distance divided by time. Because time they are equal and the distance they are not the same. So this distance on your right hand side is shorter than the distance 2. So that means the object will move slower at distance 1 and will move much faster at distance 2 because the distance is high, is bigger than the distance at the 1. Okay, next slide, please. Next slide. Are you still there?
Are you there?
Okay, next slide.
Is it this one?
Yes, fine. Thank you. So now we go to the last row of Kepler. Oh, no, go back. Thank you, that one. So the last law of Kepler states that the square of periodic time of the orbit is proportional to the cube of the mean distance, which is the semi-major axis. So you have on the figure, you can see semi-major axis, which is A. So A cubed will be directly proportional to T squared. T is the period of the the object around that the sun in the elliptical motion. So it is abbreviated here on the figure. You can see that the t square is directly proportional to a cubed. That is the third Kepler's laws of motion when your object is traveling around the sun or Earth. Next slide, please. Now, Keplerian orbital element, we have a 60 element. You have some major axis, eccentricity, mean anomaly, argument perigee, inclination, right ascension of the ascending node. So those are most used when you are doing some mathematics. And next slide. So, for example, apogee, which is your longest distance, where on the previous figure, remember where I was showing the distance one. Distance one, it was at apogee. Your apogee can be estimated using eccentricity. So the distance is a times 1 plus eccentricity, while the perigee, which is the shortest distance, is going to be your semi-major axis 1 minus eccentricity. And the height, you can estimate also height by taking that distance, then you subtract the radius of the Earth. Then it can be done in a similar way for the perigee height. So if you want to know where your satellite is, then it's easy to calculate the position. Next slide. Okay, satellite. Now what do you do when you want to launch your satellite? So those are 13 steps which most people or most companies that launch satellite uses before. Okay, so from the time they plan to send the satellite up to the end of the life of that satellite. So number one is mission planning. You have to define the purpose, orbit type, and mission requirement. So you need to know where you want to send your satellite. That is important because all satellites, they are not the same and they are not designed the same way. So you must know where you want to send your satellite and what do you want to achieve. Now, number two, you have to design and construct, which is build the satellite structure, payload, and subsystems. So this is the most difficult part because now you require engineers to sit together and build your satellite. Now, number three is to test vibration, thermal, vacuum, and the system test. So you do all of those tests. That's number three. The stage number four, now you launch your vehicle. You choose, sorry, it is the launch vehicle selection. You choose appropriate rocket for mass and orbit. So depending on the orbit and the mass, because satellites, they are not the same size, so you need to choose which vehicle you will use. And the launching site, now transport, fuel, and integrate satellite. That is stage number five. Stage number six, countdown. You check final checks, you check fuel, you check weather verification, because if you send it during long weather, then it might not be possible to launch it, or it may not even, it may not be successful. We are going to see that later, that space weather can affect the satellite. Of course, because you need technology to understand. So the space weather can affect your technology in order to launch the satellite or other technologies. So number seven, it's the day now of liftoff. Rocket launch and initiate ascent. Number eight, you check atmospheric ascent, pass max Q, failing, and state separation. So I think you have watched some YouTube video where the satellite is being launched. So it start to spread. So some parts, they stay behind so that it can move faster and of course achieve the targeted orbit. So now number nine, orbit insertion. So upper stage places satellite into the target orbit. So once now you put the satellite into orbit, number 10 is the satellite separation. Satellite released from rocket. So you release, the last point is to get the satellite at the destination, which means it is covered by a pilot. That pilot has to be released, and then the satellite will be flying in the orbit. Commissioning, deploy solar panels, system checkout. When it is there in the orbit, you start now to deploy the solar panels, so which means you have to put them in their position so that they can be used, and then you check all the system. Now 12, it's operation, no mission operation and data collection. So you start to receive signals, or you start to use the satellite according to the mission you planned to use to. And the last stage is that the satellite will not last forever. Depending on the fuel, most of them, they depend on fuel. When the fuel finishes, it will die or it will not work. Then you have to deorbit or move to the graveyard orbit. So where they deposit the dead, I will call them dead satellites. Next slide, please. Orbit perturbation. So gravitational force affect geostationary and low orbit, which are around the 1,000 kilometer satellite in their motion. So those two affect those satellite. Effect of non-spherical Earth. Earth is not sphere. Non-uniform mass, you remember Kepler's third law, not a sphere affecting some major axis. So which means the laws of Kepler, we have said that the object, in most of cases we assume that the sun and the earth, they are sphere, but they are not. They have different structures. Earth is not oblate spheroid. This affects the orbital period and the true rotational of the orbital plane, namely regulation of the node and the rotation of upside in the orbital plane. So if you want to read more, I have attached this presentation here. You can just copy the link, and then you will find more information on about the orbit perturbations. Next slide. So now, once in orbit, you need to keep your satellite either east-west station. It is called east-west station keeping, or north-south station keeping, because some they rotate in north-south or east-west. So you need to make sure that you keep them. Geostationary satellite must be kept at 75 degrees east and 105 degrees west. That is the east-west station keeping. Inclination also has to be returned to 0 for north-south station keeping. So usually to do this, they require to consume more fuel when they are trying to fix them. So they use extra fuel to fix those satellites in their orbit. So they are saying here the NSCK maneuvers are more expensive in fuel than the EWSK, which is east-west station keeping. Next slide, please. Now, we have many mission satellites. So about 66% of the satellite that are in orbit, they were sent for a purpose of communication. So they are used in communication. The next are navigation. They are used in navigation, which is 7%. Others, 6% are used in military surveillance. Other 6% are used in other things which are not mentioned here. Then they are followed by Earth observation and remote sensing, which is 5%. Astrophysics and space physics, they use 5%. Earth science, they use, and meteorology, they use 5%. So, but you can see that a big number of satellites, they are being used in satellite communication. Of course, this is because of money. So they are making money. It's a business. Next slide, please. So now we see what is the, okay, go back. Okay, thank you there. Geostationary orbit. So geostationary means that a satellite in this orbit, it has to appear stationary with respect to Earth. So it doesn't change the position with the Earth. So it is always pointing at one place on the Earth and it moves with the Earth. As the Earth rotates, it stay fixed in that location. And this has advantage, of course, and disadvantage. So at an altitude of around the 35,786 kilometer, they travel at the speed of 11,000 kilometer per hour. The satellite rotates at the same speed as the Earth. Its rotational period is 24 hours. The orbital has to be a circular, so it goes in a circular orbit. That one is a special case of ellipse, of course, where eccentricity is equal to 0, and the inclination of the orbit has to be 0, so there is no inclination. Next slide. Advantage of those satellites in geostationary orbit. There is no need to track the satellite periodically. So because they are stationary, you don't need to check them, their position or if they are where they are. So no need of rotatory antenna, reduce the cost. So they are cheap to run because they are already fixed. Then this satellite can cover around 38% of the Earth's surface. So when they are there in the space, they can see almost a third of the Earth. So one satellite can monitor a third of the Earth at this elevation of 5 degrees. This means that only 3 satellites in this orbit are needed to cover the entire Earth. So the Doppler shift is minimum because you remember, the Doppler shift depends on the frequencies, so and the distance between the two objects. So because these satellites are not far away, so the Doppler shift is minimum. No inter-satellite handoff and permanently in view. So that is the advantage. Now we can go to the next slide. So the disadvantage now, they are not, they are also, they have advantages. The 86 kilometer orbit implies long transmission lengths. They have a weak signal. So when you receive their signals, they are very weak. And of course, because they are rotating around the equator, they intend to have a poor coverage at high latitude. So when, high latitude is from 60 degrees up to 90 degrees north or south. So beyond 77 degrees, they have a poor coverage. So that is the advantages. Next slide, please. Now, prograde orbit, satellite moves in the same direction as the Earth's rotation, which is supposed to be, so those are non-geostationary. So those they don't orbit, they are not fixed. So they can move faster or slower than the Earth's rotation, which means you keep on tracking where they are to know the information or where they are getting the information from. So they are divided into 3 parts, which you have here: prograde orbit. Satellite moves in the same direction as the Earth's rotation with this inclination, which is between 0 and 90 degrees. Retrograde, they move into opposite direction between 90 and 180 degrees, and high elliptical orbit, they move at between 18,500 and 35 kilometer altitude. Satellites in this orbit are designed to give better coverage to countries at both poles, south and northern poles. Next slide, please. So now you have a medium Earth orbit. This is circular orbit, not necessarily above the equator, so it can be anywhere, but it's a circular orbit. Low Earth orbit, this is around 2000 above the Earth's surface or on the Earth, but also it is not the same as the geostationary orbit. Next slide, please. So advantage of low Earth orbit, they are very, as you can see, 2000 kilometers, they are very close to the Earth. It's easy to launch, so you don't need a big rocket to launch very far away. So you can use airplane or booster launch, reduce pass loss, lower power, lower cost satellite. So you don't need a lot of money to launch it. So they say here between 0.5 and 2 million US dollar. Shorter transmission delays. So delays, they are shorter. That is advantages. Go to the next slide. But they have also disadvantages. So they can only be visible for 15 minutes. There are many, which is large constellation. Radiation effect, reduce solar cells and electronics lifetime. So we are going to see that particles, they cause problems to satellite. So especially for those ones between this range, they end up by causing the satellite to reduce their lifetime because of the solar cells which are damaged. Next slide. Now, element of satellite launch. So I'm not going to go through all of those 29 parts or element of the satellite launch vehicle. But the most important, I want to talk about the last one because this is where all of them, or you can see the figure on your right hand side. So there is the last on the top, the last small part which is showing a satellite. That is your satellite which gives you all information you want to use or what you want to use. Other parts, they are constructed to help the satellite to achieve its orbit. Either they are carrying fuel or they are carrying the other things which helps the launching process. Next slide, please. Okay, satellite configuration, stabilization, and life. So positioning is corrected within plus or minus 0.1 degrees. A satellite life depends on its fuel. Of course, if you have a big tank, your satellite will last longer. So its capacity is in average 13 years. A satellite can last up to 13 years, but they can also last for shorter. Less position correction can extend its life. Of course, most of them, they die because of correcting their position. So when they're adjusting their position, they use fuel to adjust to correct their attitude and positions. But with this time can be extended by minimizing the correction. So they are saying that it can deviate by 16 degrees in north-south direction within that 13 years. So if you allow it to deviate by 3 degrees latitude, that three degrees can add 3 years to its life because you are not consuming its fuel when you are doing that correction. So that means less correction, the satellite can live longer. Next slide, please. Now, satellite components. So you have a propulsion system, telemetry, attitude control, you have a fuel, you have a batteries, you have a power and thermal control, and you have a solar arrays. So here you can see on the image, of course, when you want to use satellite, you have to send signal up in space. Those ones, they are called uplink frequency. That frequency is always higher than the downlink frequency, depending on the medium. So if the medium has some irregularities, of course, you are going to have some delays and the signal may bend or may be absorbed or attenuated. Those kind of things, they reduce the frequency and then it becomes shorter or it becomes shorter than the one which was sent. So that is why here they are saying that the downlink frequency is always lower than the uplink frequency. Next slide, please. Now, space segment. A satellite communication system can be divided into two segments. You have a ground and space segment. So for space segment, you have satellite and facility needed to keep the operation. So those are called the telemetry, tracking, and command facilities. So those facilities are on the ground. So they help to track and command the satellite to give the information to satellite how it can give us the information. So they keep on monitoring and using those facilities to control the satellite. So the figure here to your right is showing that satellite communication for coverage, space and ground segment. So you have both the satellite which is in space, of course, and the receivers on the ground and other things that can help you to achieve the target of the satellite. Next slide, please.
Yeah. Hello, Dr. Likens.
Yes.
I wouldn't know how the lecture was prepared because we also have to give the students a room to ask some few questions before we go for break. So,
Yes.
but I still continue to run the slides.
Uh-huh.
Otherwise, if you intend to continue this part after the break, then we may pause for students to ask questions.
Okay, it's because we have had some delays at the beginning. So I was, I think, came to end, I think, on slide 50 something. There was a
Yes.
break there of 30 minutes. And but it's fine. We can have questions.
Okay.
Then,
Just to be sure of how you prepared it, so that because you don't need to do that all the lectures at once.
yes, yes, there is a,
Because
there is a, there is a break, I think.
okay. Let me go on.
Yes. Okay, so now the space segment, the payload is the equipment that provide the service. The bus is the vehicle carrying the payload and other subsystem required for service. The transponder provide the connection link between the satellite transmit and receive antenna. Next slide. So spacecraft subsystems. You have your power subsystems, attitude orbital control subsystems, telemetry tracking command subsystems, communication subsystems, and antenna subsystems. So the figure on your right shows the same thing, that satellite already has antennas, it has the thrusters, solar panels, it has a star tracker, camera, and other things. So you can go to the next slide, please. Now, attitude control. The attitude of a satellite is its orientation in space against the disturbances torque. So when the satellite is in space, of course it faces the disturbances. So in order to adjust, it has what we call attitude control. These include gravitation, those which can disturb the satellite, gravitational field of Earth and Moon, solar radiation, and meteorite impact. The control is done to ensure that direction antenna point in the proper direction. To find any deviation or shift in the satellite orientation in space, infrared sensors are used. Those sensors are called horizon detectors. Any shift in orientation is detected by any or more sensors, and the corresponding to control signal is generated to activate a restoring torque. Next slide. So this the image shows that whether you have a three dimension, you can rotate. If the rotation is done on one of the axes, of course, you from the angular momentum or torque, you remember the torque. So the other part is going to shift in the direction perpendicular to the rotation. So that is how they use to control the attitude of the satellite. So they can use those three axes to adjust the satellite in its orbit. So of course you have a passive and active. Next slide, please. So passive attitude control is done without putting drain on the satellite energy supplier. For example, spinning stabilization and the gravity gradient stabilization. Spinning stabilization is often used for communication satellite. Active attitude control is done without stabilizing torque to resist the disturbances, torques, momentum wheels, electromagnetic coils, and the massive explosion devices are used. Electromagnetic coil uses earth magnetic field and current carrying coil. The current is controlled. Next slide. So this is what they call spinning satellite stabilization. Of course, you see the cylindrical part, if it is spinning, also it helps in controlling the satellite. So they say it uses the cylindrical satellite. Spinning is initiated during the launch phase using small gas jet. When there is no disturbances, torque, the spinning satellite will keep its correct attitude relative to the Earth. Disturbances spin will decrease the satellite spinning rate and the direction of angular spin axis will change. The rate can be increased via the impulse type thruster or jet. Next. So you see those wheels here, I'm not going to talk too much, but you have the three wheels, which are also in three different directions. Depending on where you want to position the satellite, you can rotate maybe the one on the bottom or the one on the left-hand side, on the one on the other side. So whichever wheel which is rotated, it helps the satellite to shift. So that is how they control and stabilize the satellite. Next. Now thermal control, thermal radiation from the sun, Earth, and Earth reflection affect the satellite. The Earth and Earth's thermal radiation generally affect the low Earth orbit satellites. Their impacts are negligible for geostationary satellites because they are far away. To control the satellite temperature, these are used. So they use thermal blanket, radiation mirrors to remove the heat from communication payload. Heaters may be switched on when transponders are off. Next. Okay, I wanted to stop from here. So when we come back, we can continue the second part. So now we can have a few questions and then take a break. Thank you.
Good. Thank you so much, Dr. Ali Krens, for that marathon lecture. I hope our participants are there and they have got a lot from what you taught.
Thank you. I
So
think you can hear.
now we can interact with the students, and if you want to ask a question, you can just raise your hand so that we can recognize you. I can see Julius. Julius, you can ask your question or your comments.
Okay, thank you for the presentation. Of like three questions. The first is regarding the east-west and north-south keeping, the one you explained. So are thrusters used to initiate the keeping, or like I don't know how to put it, but because if you said they rotate, right? So and then Is the transmission from the satellite itself, like, is it does it take longer? Because if it's rotating, then there will be periods when, like, how do I say, the transmission is not picked from Earth.
I think let us go one by one. I think it's much easier.
Yeah, I think it's better.
Yeah. So you say the east, west, and north, south keeping.
Keeping? Yes. Is it
So
initiated, or as in, how does it come about?
I have spoken about the attitude control. So in attitude control, the people on the ground, they will see that the satellite is shifting. So there is a way they can see that the satellite is shifting. Then in that way, they can use fuel because the satellite also has fuel. So they can command that satellite to use fuel to fix that direction. Either if it was in east, if it is shifting from east west, they will try to bring it back to its normal direction. So that
Okay.
is, it doesn't mean that it is initiated when it is launched at the same time that they are going to change. No, it takes time to shift. But once they see that it has shifted, they try to bring it back using its fuel it has already because they can actually even switch it off and on. So that's why actually sometimes that's how they if you are paying, if you have a service, if you, then you are not paying, they can even disconnect you. So they control it on the ground.
Okay.
Number two.
It's pertaining the transmission from the satellite to Earth. So
Mhm.
do we get periods when, um, because it's rotating, you don't get transmission, or how is it? How is it handled
Uh, your transmission from.
from the satellite that is in orbit?
Mhm.
And like, how if it's rotating, I would believe maybe there will be periods when there may be no transmission because it's tilted, or I don't know.
Okay,
How
we are
does
going to see. I think there's a time when you don't see the signals, you don't receive the signals. I think I have one slide where you spoke about the eclipse. So sometimes you have eclipse where the signals you don't receive the signals depending on its position or depending on where it is. So maybe that is what you are trying to ask.
Oh, yes.
Okay, so I think later we are going to see one. I have one slide about that.
Okay,
Okay.
then the last one is regarding gravity. If because from some of the figures you showed, the orbits look kind of eclipse or
Yes,
ellipse. Yes.
ellipse.
So, uh, what's the effect of gravity? Because there will be periods when it's like far from the gravity. I don't know.
Okay, so now to answer your question, they are far away from. I understand. You are saying that if the Earth has a gravity acceleration. Now, the satellite, they are far away from the gravitational field.
Yes.
So you want to know how is the gravity involved in between the satellite and the Earth?
Oh, yes. Could it be that the thrusters corrects things? I don't know.
So I think only something which is involved here is gravitational force. Gravitational force is the force between the two bodies, the two objects.
Yes.
So this object number one has a mass, object number two has a mass. And because of those masses, depending on the distance between them, then there is a gravitational force, which means gravitation, it has to rotate one around the other one, or they are pulling each other. So that gravitational force, it of course, from that is where Kepler's law is involved. It said that when the object is surrounding another one, is rotating or is making a motion around the other one has the motion has to be ellipse. where the other one, which, or in most of cases, the bigger one, it has to be staying at one of the focus of the elliptical path.
Yes.
So that is, I think, the answer I can give you. But I don't think that the gravity of the Earth is involved beyond the launching, because once the satellite has overcome the Earth's gravity, it is no longer controlled by that gravity of the Earth.
Okay, thank you.
Okay,
That'll be all
I
for now.
think that's good. Let's hear from another participant. I saw Chinedu raising his hand. Chinedu, are you still interested in your question?
Oh, yes, Prof. I'm still here. Okay.
Good.
Thank you so much. Thank you, Dr.
Okay.
Ali, for the lecture. I think I have a few questions, and you've answered some of them. So I'll just mention something you haven't answered. But speaking
Okay.
of um, attitude control, I was wondering, how do we do precise orbital launches when we want close by or distant orbits? How maybe you can give a basic explanation of how we do precise orbital launches. For example, when we want the orbital inclination to be zero for the geostationary orbital satellites. I mean, how do we do such things? That would be my first question.
Okay,
The
maybe let us start by that one.
Okay.
That one I think is technical question, because there are people who are specialists in that domain who already and know that if you want to launch this satellite at this particular or to put it in this particular orbit, this satellite has to maybe to weigh this much, or has to start at this speed, depending on. So there is a lot of technical skills you have to have in that regard. So I'm not sure if I'm able to give you a correct answer, but there is a way which is determined, and the specialists in that domain, they do that.
Okay. Thank you. I correctly understand the
Yes.
answers. So the next one would be um how do we deorbit satellites, or I mean taking them out of orbit or sending them to graveyard orbit, as you mentioned. And where is graveyard orbit? Because it seems there are satellites everywhere. Then where is
Yes,
graveyard orbit?
okay. So of course, the most of satellite that are sent in space, most of them they never come back. Actually, this is going to be a future challenges, because we will have a satellite debris. A lot of satellite will be remaining floating somewhere, but there is a place in space where they just throw those satellites that are not needed. So I don't exactly know the altitude, but they just put them. The way you see the way they control the fix the altitude, or they change direction. They can even shift the satellite from one orbit to another one, depending on the objective they want. So from the ground, there is a way they can control orbit by maybe, I'm not sure, but by maybe using fuel, then it can maybe accelerate from one position to the other. But they can always control it in the space.
Okay. The
So
last one.
the same way they used to control to track the orbit, I think is the same way they used to remove it from the orbit. Some actually, but recently you saw that the American guy, they were able to bring back some of the payload from space to the Earth where they launched them. So by technology you can control, but I don't know if it is done from satellites that are far away, but it can be. At this point, I think when the satellite finishes its life, I think they send it to another space which is far from the normal orbit.
Okay.
Okay.
One thing,
Let's.
what's the probability of satellites colliding? How probable is that? Satellites, if there are so many of them.
No, I think the probability of colliding is low because the space is too big, but it is there, so they can collide. And but it's low, it's not that high. Depending on the orbit, of course. If they are low, if they are in low Earth orbit, the probability is higher than others because it depends on the constellation. If there are many, the probability is high. But also I don't know the exact probability, but I think the probability must be low.
Okay, thank you very much.
Okay.
Okay.
Let's take one more question and then we go for break. We continue after the break. Let's take one question from Ned. Ned, are you there?
Yes, thank you, sir. Thank you, Doc. My question is very simple and straight to the point. You've answered part of it, but what I want to know is that for the lifeline of a satellite in space before it is confirmed to go to graveyards, what's determine that lifeline before it is confirmed? Is it morphology, or when the fuel is exhausted?
Oh, so okay, the lifetime is controlled by fuel, so they can check where the amount of fuel which is left. They know, they will know that this fuel is not going to last him for. They know how it uses fuel, so they can know that this one is going not to last for the next year, for example. So then they will know it is approaching its life end.
Okay, thank you, Doc. But that means the quantity or size of the fuel will
Yes,
be imputed to determine the lifeline of that satellite to
yes,
achieve its objective before
yes.
it dies out.
The more fuel and of how it use it. If you are using it to correct the attitude all the time, it will finish very quickly. But the rate of how that satellite uses that fuel is the one which determine its lifetime in orbit.
Thank you.
Okay. I think we have tried for this segment. We can allow Dr. Ali Krens to take water and tea, and then we bounce back for the second segment, maybe in the next 25 minutes. Let's
Okay,
come
that
back
is
by 12:55 so that we can complete the second segment. Let's go and have a little rest. We have all participated actively, and I appreciate everybody who is patient up to this moment, taking part in this summer school. So thank you.
thank you
We
so
go for
much.
break. Yeah.
Thank you. See you.
Thanks.
Well done, though. You found it.
Okay. Yeah, to come and force this. Yeah.
Head office. At your place where there are other people. Yeah, they are there.
Well, no, this year, people will come. People are on their respective offices.
Yeah, they are in their viewing it.
But since I don't have computer, I have to
Yeah,
come
come.
to represent.
Some of the questions in the chat. But I'm not sure if Aman is around. He was asking questions from the chat. Maybe I can be discussing him while waiting for others.
Aman, are you still there?
Yes, I'm here.
Thank
Good.
you.
I think he wants to discuss your question.
So I think you were saying how network problems. Okay, how do satellite launch vehicle launch and how do they put satellite in orbit? So yeah, I think I have briefly spoken about it. So the satellite is launched using a satellite vehicle, which is I think it has a different element, which are about the 29. I think I have shown to around 25, 29. So each of those components, they have stages where they have to be released from the main part of the vehicle. So of course, initially from the ground, it will be very heavy. Then once it reaches a certain altitude, they release a part of it. Then it becomes lighter, lighter. Then as they continue, at the end, you will have the payload, which has a satellite itself, and they will separate the payload from the satellite, and then try to open the solar panels and the other setup. But initially it must have a lot of fuel to initiate the action force. The action force pushes the ground, and then the ground pushes the vehicle in the opposite direction using third Newton's laws of motion. And of course, I think someone will present about the escape velocity, which is the velocity necessary to overcome the gravitation, the gravity, the Earth's gravity. So, but I didn't put those information in my slide. But depending on how heavy the bus is, then you need to apply the force depending on on the weight of the whole system. I think maybe let me see if there is another. How electromagnetic spectrum helps satellite transit signal to ground station, and how does the ionosphere delays affect satellite signal transmission? So, okay. Of course, when you use your device, either your communication device or any other thing, you use electromagnetic wave. So those electromagnetic waves, they travel at the speed of light. The satellite has to receive the electromagnetic signals and then send to the receiver your message or your signals. But in between, the electromagnetic wave can travel at the speed of light if there is no medium in between, if it is in a vacuum. Because we have gases, we have ionosphere, we have other particles. Those particles, they interact with electromagnetic waves, those signals. That is now where you are asking about the ionospheric delay or ionosphere delays. It is because when it pass through the irregularities, which are the higher, the region where the electron density is higher than the background, then the signal may be uh, attenuated or may be absorbed or it may be bent because the electron density, it acts like a refractive index. So that refractive index, it may change the speed, even the speed of the wave. So of course it reduces the speed. Then that speed, when it is reduced, that I think that is what we call delay. So it changes the time it takes. It is not exactly equal to the speed of light. It is reduced. Then you can say that there is an effect of ionosphere on that signal. I think that is the first comment. Let me check the other comment. I don't understand how the ground station, the satellite. Okay, I think I've touched on that. And technology, please explain the link and please quickly summarize the first part of. Okay, I'm going to give you the summary of this presentation at the end. What causes satellite to deviate from their original path? So I think this is Mulambya. Is Mulambya around?
Yes, I'm around.
Okay, so you're asking what causes the satellite to deviate from the original path. So
Yes,
we've seen
because
that, yes, in the slide we have seen that we have a gravitational other bodies like moon, like other planet, asteroids, and other things. And we have a drag, we have a neutral particles. So all of those things they disturb the satellite in its orbit. That perturbation then may end up by deviating its path because they are pulling, other objects are pulling through the gravitational force. And also depending on where it is passing. So the disturbances, they are the one which causes the satellite to deviate. And then people on the ground, because they put in that path, there is a reason why. So they have to check if it is deviating and then use its fuel to fix that, to correct the attitude.
okay, thank you.
Okay, so I think now we are going to continue, but what fuel is used when it's in orbit for correction thrust? So they put the fuel before they launch it, so it has it already. So it uses the fuel it has. It has a capacity. Each satellite has a capacity depending on the money you pay. Of course, if you want to last for longer, you pay a lot of money. So it has the fuel already when they launch it. I think now we can continue.
Yeah, yes, I
The
think we
next
can
part.
continue
Yes. Then we can have more questions at the end if
at the end. Yes,
when
yeah, I
I'm
think it's
done.
better.
Okay. So
So,
now I was talking about the telemetry tracking and command subsystem. So this subsystem is essential for the successful operation of a communication satellite. It requires Earth and space station to control the orbit attitude of satellite, monitor the status of all the sensors in the satellite. So you can switch on or off in communication system using the TT and C. So TT and C, that is what they use on the ground actually in the ground facilities to switch on or off to control the satellite. So this figure shows the space. You have your satellite in space and you have other things that are on ground to help the satellite operations. So go to the next slide. Now telemetry. So in telemetry, sensors are used to monitor the fuel tank pressure, voltage, current, temperature, status of each subsystem, and switch positions. Attitude control and etc. Data from all sensors are sent to the telemetry unity to be converted into digital data before being transmitted. So they use those technical words which are FCK and or PCK are in the transmission. Next slide. For tracking, of course, they need to know the location. A satellite tracking is done when it transmits beacon signal to its TTC station on Earth. Tracking is important during the transfer and the drift orbital phase of the satellite launch. Its position will tend to shift due to disturbances torque. So now that person, I think, is now answered. Someone who want to know the disturbance torque. They're the one which shift the satellite position. Therefore, it is necessary to track its movement and send the required correction signals. The satellite range from the ground station also need to be tracked while in its orbit. This can be done via the measurements of the propagation signal delay. Due to the complex operation of the TTC, we need both ground and the space facilities. So both are used to operate the satellite. I'm not sure if Musa, do you have a question? Your hand is up.
Yes, I do. I do have a
Oh,
question.
sorry. Okay, you can ask your question.
Okay, I hope it will not interrupt your flow.
Okay, if it is complicated.
You can drop the question, let him keep.
Okay, ask me a question.
Okay. Thank you very much for your presentation, and then your slides. They are very, very easy to interact with. My name is Musa Emmanuel from Center for Business Space Science and Astronomy here in Sudan.
Okay.
So, you talked about the eccentricity.
Yes.
As related to different satellites, especially for that of the geostationary satellites. Okay. So,
Yes.
but you didn't mention that of the polar Earth orbiting satellites that come at us from the north and southern poles, because I've done some little work trying to track them. So, my question would be, what is the eccentricity of the polar Earth orbiting satellites?
Eccentricity, okay. Actually, the geostationary orbit, they are not, they are a special case of ellipse, if I would say, because they form a circle. They travel on a circular path, which is for your eccentricity. Eccentricity is 0 because A and B, they are equal. But for the polar orbiting satellite, they move in a ellipse, which means your eccentricity is between 0 and 1, where the Earth is going to be at 1 of the focus, which means at some point, I think someone is talking in the background. Can you please check if everyone is muted? Okay, thank you. So, for the polar orbit satellite, the Earth has to be at 1 of the focus of that ellipse, which means sometime the satellite will move close to the Earth, and the other time it will move far away at apogee. But at perigee, it will be very close to the Earth. I think that is what you were asking.
Yes, that would be my question.
Thank you.
Thank you
So
very much.
now, I think someone also has asked about the satellite being not seen or being off for some time. So this is what we call solar outage caused by the solar eclipse. You remember that the satellite, they use solar panel. So sometime then the Earth is shared, or it hide the sunlight from the sun to reach the satellite. So when the Earth is between the sun and the satellite, the solar panel do not get solar power. This happens twice a year, and they are called vernal and autumnal equinox for about 6 weeks each year. So on the day of equinox, satellites are in the Earth's shadow for a few minutes to about 65 minutes. So that means solar panels in this time, they will not be available. So you have to use other means to be able to operate the satellite. So that means you have maybe to use the batteries or fuel. Go to the next slide. Multi-access system. So now, how do people access the satellite? There are different ways. The source of some transponder of frequency channel is shared by 2 or more stations on Earth through multi-access system application. So they are called multi-access system application, which are divided into those families: FDMA, TDMA, CDMA. We have also SDMA, which is space division multiple access, that uses frequency spectrum through multiple spot beams on satellite. So FDMA stands for frequency division multiple access. Every user is assigned a different frequency band with the satellite transponder. For TDMA, which is time division multiple access, all users share the same frequency but transmit in different time slots. ACDMA, code division multiple access, all users share the same frequency and transmit at the same time and in the same beam or polarization. But each user, each one use a unique spreading code to separate signals via high-speed spreading sequence. Next slide. So now I'm going to talk a little bit on the artificial intelligence. Artificial intelligence is used in satellite operation. So I have here a list of those artificial intelligence. I did not want to go to details, but you have machine learning, and you have other models like neural network and others which are used in satellite to remote sensing data analytics, satellite trajectory planning, and collision avoidance, satellite health monitoring, satellite communication, deep space, and multiple planetary exploration. So they use AI to do those activities on the satellite. Next slide, please. Okay, now I'm going to spend some minutes talking about the space weather and how do they affect the satellite in their orbit. So first of all, let us start by defining the space weather. So space weather, you already know, most of you, the terrestrial weather, which is sometime you will have a heavy rain, it will be sunny, it will be winter or cold and hot. So those are terrestrial weather. But in space, we have a similar weather, which is, of course, not the same as the terrestrial weather, because the terrestrial weather, you can see it with your eyes. But the space weather, it is not possible. Most of the space weather phenomena are not seen by your naked eyes. So you need a specific instrument to observe the weather from the space. So here the definition says that space weather is defined as the condition on sun and in the solar wind, magnetosphere, ionosphere, and thermosphere that can influence the performance and reliability of spaceborne and ground-based technology systems and can endanger human life or health. So examples of those the phenomena which come from the sun, we have what we call coronal mass ejection. This is a massive sudden release of plasma and magnetic field from the sun's corona into the ionosphere. Solar wind is a continuous high-speed stream of charged particles, primary electrons and proton and alpha particles, escaping the sun hot outer atmosphere, which is corona, into the solar system. So that is, we have now coronal mass ejection and the solar wind. The other phenomena which occurred on the surface of the sun is called the solar flare. So a solar flare is a massive sudden explosion on the sun's surface, releasing intense bursts of radiation, light, X-rays, radio wave, and high-speed particles caused by sudden release of energy from twisted magnetic field, often near sunspot. So this solar flare, they usually travels at the speed of light from the sun to the out space to the surrounding space. Next slide. Next slide, please. Okay, thank you. So during the first International Polar Year in 1882, simultaneous observation of the aurora and magnetic field of the Earth at both poles contributed to the recognition that there must be electric current in the ionized upper atmosphere of the Earth. So this image on your left side, it is showing the aurora. So during this time, that is where they had a meeting and then say that there must be electric current in the atmosphere. So which linked the aurora to changes in the Earth's magnetic field. So modern investigation of the heliophysics and space weather are rooted in the first international polar year. So during this time, that's when they started to think about space and how the influence it may have on the technology and other stuff. So they were in this meeting with 400 scientists attending. Next slide, please. Okay, now what is the drivers of space weather? So this is the image of the sun taken by one of the satellites. Of course, you can see those black spots. The black spots are called sunspot. Sunspots are a concentration of magnetic flux associated with open magnetic field lines on the surface of the Earth. So those sunspots, they appear dark because they are cooler compared to the surrounding area. So they have a temperature between 3,000 and 4,500 Kelvin, while the surrounding area of the sun, it has around 60,000 Kelvin. So you see now they are cooler than the other side. That's why they look dark when you look them on this kind of image. Next slide, please. So most of solar flare, as we have seen, most of solar flare and the coronal mass ejection originate in the magnetically active region. So the sunspots, they always generate those solar flares and the coronal mass ejection. So if we are going to make a comparison, those sunspots can be compared to the volcanoes on the Earth. You know, volcanoes, they can erupt and then you get magma and the other things from inside the Earth. So the sun also has those sunspots where they can erupt coronal mass ejection and solar flare. You can see here on this image, they are comparing their size and the size of the Earth. On the bottom left of the figure, you can see the size of the Earth and also the size of the sunspot. So then how do space weather centers monitor the sun? When they have many sunspots, they expect to have more activities on the sun. And that is how actually they warn people. They say, we see that there are many activities within a few days or few years. They will know that they have to expect more activities on Earth, or many activities will affect their electronics or their satellite, anything which can be affected by the sun. Next slide, please. So coronal magnetic loops, as you can see on this figure on the top, there are loops of magnetic field extending more than 30 times the diameter of the Earth above the surface photosphere, are recorded in extreme ultraviolet light by the TRACE, which is a Transition Region and Corona Explorer satellite. This was launched in 1998. The solar cycle is based on the number of sunspots. As I have said, the sunspot number, so they have been recording the sunspot on the sun. They will say maybe this today we have a 20, tomorrow 40, tomorrow after tomorrow 60, something like that. Then they found that the sunspot number increases and decreases every 11 years, which means that cycle repeats every 22 years, which is associated with the reversal of the sun's magnetic poles. So magnetic poles of the sun, it rotates, it changes every 22 years. That is why we have that sunspot now, that the solar cycle. So the peak of the recent solar cycle took place in October 2024. That is when we had the solar maximum. And now it is declining. It is reducing to the solar minimum. So the solar minimum will come, I think, in 6 to 7 years. Next slide, please. So this image shows the bottom figure shows the sunspot numbers, the daily average sunspot numbers from 1880 up to 2010. So, and the figure on the top shows the regions on the sun where the sunspot number were recorded in the same intervals. So this image shows that the both north and southern hemisphere at mid latitude, that is where you have many sunspot. So they are forming this butterfly structure, which is of course, which shows us that that's the region where people, when they're doing forecasters, that is where they look to see if they are going to see the sunspot so that they can warn people of something that may come from the sunspot. Next slide, please. Okay, now we have the sun and the earth. How does the space weather affect our environment? So this figure, it shows the first panel. You see that this is the sun. From the sun, you will have a corona hole, what you call corona hole, large scale instability, which triggers corona mass ejection. And those, of course, you will have active regions and you will have solar flare from the sun. Now, the distance from the distance on the surface of the sun up to the magnetosphere, the medium is called interplanetary medium. Within interplanetary medium, you have a plasma, where that is where you have a corona mass ejection shocks, radio flux, EUV flux, X-ray flux, energetic particles, galactic cosmic rays, and others. So now the next part is magnetosphere. Magnetosphere is the region surrounding the Earth where the magnetic field it shields the Earth and everything that is within that magnetosphere. So here, that is where you have what you call geomagnetic storms and substorms. Of course, you have also in this region, you have what you call radiation belt and particles. Now we talk about the ionosphere. When you go deep down, we are coming toward the Earth. In the ionosphere, which is your region from 50 kilometer above the surface of the Earth up to 1,000 kilometer, this is where you get aurora electrojet, ionospheric scintillation in the ionosphere around the 400 kilometer, and the ionospheric disturbances within the ionosphere. And then below or within the ionosphere, you have a region which is called thermosphere. Thermosphere, you understand the word thermos, which is thermodynamics, temperature, so they are associated. So it's the region where temperatures start to increase. So this is where you get heating, expansion. Now we get to the Earth. On the surface, the sun can affect the surface by creating what you call geomagnetically induced current. So this is not the topic of today's presentation, but it is to show that space weather can affect our technology and the other stuff on the Earth. Next slide, please. So the space weather is measured using the index. So for example, solar activity, they can know solar activity if the solar activity is high or low. How do they do that? They use sunspot number. Sunspot, you remember there is sunspot, and now they can count, oh, we see 2 sunspot number, we see 3, we see 4, we see 5. So when the number is greater than 250 on the sun, they say there is extreme condition. Solar activity is high, extreme, sorry. And then when the number is between 150 and 250, it is very high. When the number is between 80 and 150, it is high. 40 to 80, it is moderate. 20 to 40, it is low, and 0 up to 20 is very low. So then on our Earth, they use index which is called the AP or sometimes KP. When this index is greater than 100, they say it is a severe storm. Of course, it is measured based on the coronal mass ejection. When the coronal mass ejection hit the Earth or hit the magnetosphere, it reduces the Earth's magnetic field. These indexes are estimated based on the magnetic field which is reduced, and also based on the current that is caused by those activities on the magnetosphere. So when the index is between 50 and 99, we say you have a major storm. When it is between 30 and 49, you have a minor storm. When it is 16 to 29, you have active. 8 to 15, unsettled, and 0 to 7, it is quiet. It is like normal. There is nothing happening. But this index AP can be converted to KP when KP it ranges from 0 up to 9. And then we are going to see how do they characterize other geomagnetic activities based on the KP index. So the sunspot number can also be converted to another index, which is called F10.7. And those values can be used to convert from one index to another one. Next slide, please. Okay, so this is how they characterize geomagnetic storm. So we have 5 categories of storm or scale. G5 is the worst, or they call it extreme. So when you have a geomagnetic of G5, your KP will be 9. KP, which is the measure of how the magnetic field is affected. And power system are damaged, spacecraft surface charging, orientation tracking, they are affected, HF radio impossible for several days, and GPS degraded for days. So those are the effects on the system. So the next scale is G4. Of course, from the sun, it's a storm coming from the sun. If it is G4, you will have a KP of 8. And the power system is protective systems may trip. Spacecraft, it is the same as the G5. HF radio sporadic in places, and the GPS degraded for hours. So it is becoming somehow good, and this is called severe storm. For G3, you have your KP index is 7. Voltage problems, false alarms, spacecraft tracking, and the orientation problems. HF radio is intermittent. And this is called a strong geomagnetic storm. Now for G2, your KP is 6. Power systems, voltage transformer damage, orientation by ground control for spacecraft. HF radio are fed at high latitude, but maybe not very bad at low latitude and mid latitude. And this is called moderate storm. For the minor storm, you have a KP index, which is 5. And your power system, it is weak, power grid fluctuations, spacecraft minor impact, other system, migratory animals affected. Any question? Okay, I think someone was. Okay, thank you. So now the space weather scale for radiation storm. So we were discussing about the coronal mass ejection. Now this one is for radiation storm, because sometimes they count those storms based on radiation. So we have S5. S5 it can affect biology. I'm not going to read everything, but it can affect biological satellite operations and the other systems. Maybe let me read about the satellite only. So satellite may be rendered useless. Memory impact can cause loss of control, may cause serious noise in the image data, Star trackers may be unable to locate source. Permanent damage to solar panels possible. Those are for S5. And how long does it take? Fewer than one per cycle. So within a cycle of 11 years, you may have one S5. And the severe for satellite may experience memory device problems and noise on imagery. System tracker problems may cause orientation problems, and solar panel efficiency can be degraded. So you can have a 3 event, severe event per 11 years. Strong for satellite, single event upset, noise in imaging systems, and slight reduction of efficient in solar panel, they may take place. So how often do they occur? They can occur 10 times per 11 years. Now S2, for satellite operation, influence single event upset possible. But as they reduce in severity, they occur often. So you can see here, you can have a more than around 25 per 11 years. And the minor, which do not have effect on satellite, they can occur 50 times per 11 years. Next slide, please. Okay, now we have this satellite is monitoring the sun. It is called the SOHO, the Solar and Heliophysics Observatory. Satellite has a camera observing the sun with various filters 24 hours per day since it was launched in 1995. So that satellite, you can see its orbit around the sun. It goes exactly with the sun around the sun. So it is monitoring the sun, and that is actually the one which gives most of information about the sun and sunspot number and everything. It is at L1 point, which is 1.5 times 10 to power 6 kilometer from the Earth. Okay, next slide. So those are the event which comes from the sun and their duration. How long do they take to reach the Earth? Or yes. So for example, I know the light from the sun can take about 8 minutes up to here. And the solar flare is the same. Solar flare also takes about 8 minutes, which means it is very difficult to to give warning to the people who can be affected by the solar flare, because the time you are trying to write your warning, it has already reached the Earth, and the people, they can't do anything. But this one is used in actually it affects more in HF communication. Those who use HF communication, especially in security, military, and the other people who use HF communication, they are the one who are affected more by the solar flare. So other things which you can see here: radio noise emission, energetic particle, magnetic storms. I think magnetic storms is the most important here we can talk, which takes up to 4 days. So a geomagnetic storm can take between 1 and 4 days to reach the Earth from the sun. So this is very good because they also have many effect on satellites, on other things, on our ionosphere. So it is better to know it because they can be mitigated. So people, when they see a storm, especially using those cameras of SOHO, they can say, okay, this one is coming toward the Earth. And then if it is coming toward the Earth, they warn people so that they can take measures to mitigate their impact on Earth, because it is going to take up to 4 days to reach the Earth. Of course, they have some errors when they are warning people, but they help because in the end, they do come toward the Earth and they do some damage. Next slide, please. So this is the image which shows in general the effect of space weather on technologies. But I'm not going to go through everything. But here you see that satellite is there on the top, almost on the top. So the satellite also is damaged or is affected by the geomagnetic storm or the space weather. So on the next slide, we are going to see how they are affected. Next slide, please. Okay. So when people are trying to build a satellite, it was recommended that they must design a satellite to operate under extreme environment condition to the maximum so that they reduce the effect or the impact, because the several space weather event, understanding society and economy impact, this was a workshop which reported that because if you don't take
Hello,
consideration, yes.
I'm in store.
Oh, okay. So if you don't take into consideration of the space weather, your satellite will not last longer, or it may even fail because of the space weather. So you must take into consideration before you send the satellite, you must know about the space weather effect on the satellite. So the technique is rarely 100% successful, and space weather will typically end up impacting some aspect of the space mission. Next slide. Next slide, please. Okay, thank you. So now I think this table summarizes the space weather effect on satellite system. You have a ionosphere variation. When the ionosphere varies, the variation of ionosphere means the electron density decreases, increases, or changes depending on different phenomena that are occurring within the ionosphere. And note that ionosphere is a region between 50 kilometer up to 1,000 kilometer on above us. So this will affect wireless signal reflection, propagation, and attenuation. So communication satellite signal interference will occur, and you have a scintillation. Scintillation is a phenomenon where the signal is spread into many store signals, and then they follow different paths. So this can affect the amplitude of the signal. Also, it can affect the phase of the signal. Then the magnetic field variation, when there is of course, when there is a geomagnetic storm, this can change attitude control of spacecraft, because some of the spacecraft uses magnetic field to keep their position. Now, solar radio burst, excess noise in wireless communication system. When you have a radiation will cause solar cell damage, semiconductor device damage and failure, spacecraft charging, suffers in the interior materials. Now on the atmosphere, you will have low altitude satellite drag. So if the satellite is within the atmosphere, you may have a drag, which of course you have a friction, and that friction can cause other problems on the satellite. Attenuation and scatter of wireless signals within atmosphere. Okay, go to the next slide, please. So we are still looking at the effect. So what we call total ionizing dose, it can cause degradation of microelectronics. Those are from trapped protons, trapped electrons, and solar protons. Those they can cause this degradation. Displacement damage dose, they can cause degradation of optical component and some electronics, degradation of solar cells from trapped protons, trapped electrons, solar protons, and neutrons. Single event effect, They cause data corruption, noise on image, system shutdown, electronic component damage. So they come from heavy ions, solar protons and heavy ions, trapped protons and neutrons. Solar erosion, surface erosion, degradation of thermal, electrical, optical properties, degradation of structural integrity. So they come from particle radiation, ultraviolet, atomic oxygen, micrometeoroids, and contamination. Next slide. So that is the next part, surface charging. You have a biasing of instrument reading, power drains, physical damage from dense cold plasma, hot plasma, ring current, aurora population, which is a few electrovolt to tens of kilo electrovolt. Deep dielectric charging, biasing instrument readings, electrical discharge causing physical damage. These are came from higher energy electrons of more than 300 kilo electrovolt. Structure impact, structural damage, decompression. They come from microelectroids and orbital debris. Satellite drag, these they cause torque and orbital decay. So these are, they come from neutral atmosphere. So those, they can affect the satellite. Next slide, please. Okay, so here I was trying to show the part of the satellite that can be damaged by the storms. So you can see that you have a solar array power decrease due to radiation damage. You have a single event effect of microelectronics, spacecraft component become radioactive, electromagnetic pulse from vehicle discharge or surface behind this shielding or deep inside, surface degradation from radiation, electronics degrade due to total radiation dose, and the solar arrays arc discharge. So, okay, you can go to the next slide. So space-based communication, broadcasting, weather service, navigation, power distribution, and terrestrial communication are affected by space weather. That is why nowadays, for aviation, for example, now they require that all aviation they have to know the information of the space weather. So before they can take their trips. So other activities depending on the precise position, such as aviation, road transport, and shipping are also affected. Satellite in orbit suffer in terms of communication degradation, performance, reliability, and overall lifetime. So space weather can reduce the lifetime of the satellite. Next slide, please. Now we're going to see some applications, and then from there, we can close the presentation, and then you can ask some questions. So the satellites are used, of course, in many aspects. So this is one of the few examples I have chosen to show you, which is called video conference. So for video conference, you have this person on terminal 1. Terminal 1 send a message to satellite. The satellite system can transfer the message to terminal 2, and then terminal 2 will see the message and then send the feedback, which is that is communication. Then the feedback goes to the satellite again. The satellite send back to the terminal 1. And then people, they can interact each other using the satellite, which is, you can send audios, videos, and the other kind of information, data, anything. Go to the next slide, please. So also satellite can be used to share internet, especially in remote area where you can't easily deploy your fibers or your antennas to help you to transmit the internet. So you have the internet on your left-hand side, then you can send the internet to the satellite. The satellite can spread the internet to different remote sites. Next slide. So other application of satellite include TV broadcast, weather, military, navigation, mobile disaster monitoring, search and rescue, store and forward, mineral exploration, lunar exploration, deep space exploration. Next slide. And the satellite phone, of course, you have a satellite TV, GPS, GNSS navigation. So we use GPS and GNSS to get the data to study the ionosphere. Satellite internet, Starlink, or OneWeb, Viasat, weather and Earth observation data, military and deep ocean communication. Those are other applications that need satellites. Next slide. So now I try to check online what could be the cost of launching a satellite. So that is, I think, one of the last slides which I want to share with you before we can close. So I found that some satellite with their buses can weigh up to 7,000 kg. So imagine to lift that heavy object, it is very expensive, of course, to launch this heavy object from the ground into space. So only governments and the big companies with a lot of money can do that. So the typical weather satellite can cost around the 290 million US dollar. A spy satellite may cost around the 400 US dollar million, sorry, 400 million US dollar. To maintain and repair the satellite can cost up to 1.5 million per year US dollar. And then to launch, it can cost between 10 and the 400 million US dollar, depending on what you're using. So in general, you can see that it is not easy for anyone to dream to launch a satellite. But countries and big companies can do that. So next slide, I think it is the summary of what I have presented. So I have touched on simple communication process. I have discussed the 3 laws of motion which were established by Newton, where we have seen that the third Newton's law of motion can help us to launch the satellite, of course, through action-reaction. And now I have explained Kepler's laws of motion, which govern, of course, satellite in their orbits. They follow those rules. And of course, if people, they want to know their position, their height, whatever, they use those Kepler's laws to do the estimation. Satellite connect people through wireless communication. So there is no wire from the sender to the receiver connecting the satellite to that person. So they use electromagnetic waves. We have seen that they use those EM waves to communicate. Then I have given a brief introduction on how satellites are controlled and tracked. So we have seen some of the space weather effect on satellite. Some very few applications were introduced. And in the end, we have seen that it is not cheap to build, launch, and operate a satellite. But in general, the interest of having the satellite is higher compared to its cost. So once you have your satellite in its orbit, you get more interest than the cost it took when you were launching and operating the satellite. So from that, I thank you for your kind attention. Now I think I can take a few questions and then we can end the session.
Good. Thank you so much, Dr. Likrens. It has been very exhaustive, and our participants are also active throughout the lecture. Thank you once again. So we can now listen to our participants for comments and questions, clarifications.
Thank you.
I can see Aman. Aman, your hand is up. You have any question?
Yes, I do. I have a few questions. How does telemetry link with like the satellite, like communication and space technology? Because I still don't understand that. And if 60% of satellites are used for communication, then what is the 34% of satellites used for? And like as well, how do they determine that this is a geocentric orbit, low Earth orbit, medium orbit? How do they determine with the kilometers?
Okay, I think you can
Okay.
listen to his response.
Okay, so I think maybe you can, there is a slide when we were starting. Maybe you can go back. There is a satellite. So there is a slide. I can start with that of 66 from the beginning when I was showing the mission. He was struggling, I think, to connect, but I have explained that some of they are used uh, in astronomy, in military, in other many things.
Let me run to the first slide
To
and
the
begin
slide.
from there.
I think it is much easier to. Oh, maybe you're far. You are very far away. Go
Far
back.
away?
Down, down.
Okay.
You were very quick. Down, down. Down. That one. No, go back.
See this?
No, the other one. Go back. Go back. This one. No, the next. Oh, okay, that one.
This one?
Yes. So he's asking me about that 66% of the satellite are used in communication. So what are others? So you see, you have earth science, meteorology, astrophysics, space physics, earth observation, remote sensing, military surveillance. Of course, for military, I think they are used in guiding their missions and maybe spying or other things. And navigation, when people they want to navigate from one location to another one. Of course, now he want to know maybe others, the 60%. So that you like GPS and GNSS, we use them to study, to know what is going on in the ionosphere and the other things. So those are, apart from communication, which is 66%, others, they are in this range of the categories, which most of them, they are for education, but also you have the direction when you want to travel from one location to another one and the military. That is for 66. I think you understand now.
Yes, and the
Aman?
one about telemetry and how they determine the orbits. I asked a bit earlier about how do they determine that from 3,600 it's geocentric orbit, low orbit is 2,000 kilometers. How do they determine that?
How do they calculate that this is the, okay, how do they know that this is this kilometer?
Yeah,
Or how do they know that this is the position we want?
yeah, like how do they know that from 2,000 kilometers from the Earth's surface is low Earth orbit? How do
Uh,
they determine that?
I'm not sure if I know exactly how they do that, but I think there must be some devices tracking the position and the right ascension, declination, all of those kind of information, then the height, so it can be easily known. So I'm sure there must be some specialists in that domain, especially those in engineering department. They know exactly how they determine the position.
Earlier,
But
I
it is
also
more,
asked how is telemetry linked to satellites? How are they linked to the satellites? To satellite
telemetry.
communication and technology.
Okay, so telemetry is used to control the satellite to all of the paths. But how is it used? It is used from the ground facilities. So they will be using computers, and then from the computer they will be connected to the satellite. Then they can control whatever they want to control from there.
Okay. I think that's
And
okay.
this is my last question.
Oh, I think there was
How is
Just,
so there was
just
another
how is
question.
meteorology linked to astronomy?
What?
How is meteorology linked to astronomy, and what is attitude control? That's my last question.
Okay, wait. There was another question you have asked before about the geocentric. I don't remember.
Geocentric are saying about how do they determine each of those orbits.
Oh,
That's
okay. So
what he asked.
I have answered that one because of course they know the position of the Earth, and then it is maybe they can put even a device to track the position as once the object is moving. Now it is not even in your phone. People, they can just track where you are when you have your phone, so they can know your position. I'm not sure if they use the same, but it is easy to put a device that can show the position. So about now, you are asking, there is another question about the attitude control.
Yes. What is that?
So attitude control is they want to keep the orientation of the satellite. So if the satellite was designed to look on the Earth, and then they find that the antennas are pointing somewhere far away from the Earth, so they try to bring back the antennas so that they point where they're supposed to point. That is what they call attitude control. And
And
also
the other part was how is meteorology linked to astronomy?
okay, meteorology.
Yeah.
Of course, I think that question is going to be somehow complicated, but I understand that astronomy is the study of stars, which are stars. Some of the stars, they are far away from us. And I know that the nearest star is the sun, which is far away from the Earth, but the asteroid, those the stones, they are, I think they are in the solar system. We have many of them, which a solar system, I think, is a part of the astronomy because from the Big Bang theory, everything was, I think, was expanding, and then some objects were born in between, and then so I think asteroids, they are a part of astronomy. So the
yeah.
astronomy
I
is
think
bigger
you have
than
answered
the.
that.
Okay, thank you.
It's all right. Can we just take one more question and then we end because we want to leave exactly by 2, though we have even added a minute. Do you still have your question? That should be the last question we take.
I think
Yes,
Daniel.
thank you very much, Professor, for that opportunity. I was looking at
Thank you, Professor.
if anyone within the organizing community can touch on the kind of regulations that governs launching a satellite by organizations or companies that actually that's their business. Because we have a whole lot of CubeSats from different institutions. I mean, how do they go about? Is it that you just build your own, or you just launch it to orbit? Because I understand there are regulations around it. So if someone could touch on that so that other people can benefit from that space.
Thank you. I'm not sure if I'm going to answer that question because that is a political question, or but someone maybe here if has information can help us. But I'm sure you can't just come in the morning and build a satellite and say I'm going to launch. You have to go through some system. You have to meet some standard because at some point you may find that you're not able to launch successfully your satellite, and it may come back maybe and hit some people and may kill people. So they must know if you are able to do that. Also, you must meet some standard. You must have some international standards approving your applications, and then I think you must have some other rules saying that maybe once your satellite is no longer there, you have to put it
You
into
orbit it.
debris, something like that. But there must be a body
Regulations.
governing that part. I'm not sure if there is someone who knows better than what I know who can explain to us.
Yes, what you have said, is in order. United Nations Office on Outer Space is actually the regulatory body. For
Okay.
each of these satellites you want to launch, you can have a conceptual idea of your mission for which you want your satellite to achieve. It could be educational satellite or monitoring or navigation or weather or communication. How you package it, yes, you can have those concepts and you can build that in your lab. But when it comes to putting it in space, that's where the regulation comes in. I mean, then you take it from there. United Nations Office on Outer Space, that actually take care of determining the orbit where your satellite is going to be, such that it's not going to conflict with an existing satellite already in the orbit. And they also look at your mission, make sure there's no conflict of interest out there. And also the timeline, the time, the space your satellite will be, the period, and possibility of deorbiting it. I think you are right in the way you mentioned it. Thank you for the good.
Thank you also for the additional information. Thank you so much.
Thank you for that input. I think at this point we have to draw the curtains, and I wish to thank Dr. Ali Krenz for making out time to be here with us. I appreciate all our participants.
Thank you so much. I think there was someone who was asking about the slide. I'm not sure if you can maybe share the slide to them.
Usually we make the slides available on the website for any person who is interested to view and maybe go through it again. And of course, the recorded video of this presentation will always be there. So we are going to upload all of them on the website. So they will be available there before the end of today, I think, or before the next lecture. Everything about today's lecture will be online. So you can just go to the site and then see what is happening there.
Okay, cool. Thank you.
Good. Thank you so much. If you have further questions, we will make his email available so that you can communicate with him, and he will clarify on whatever concerns you have.
Okay,
so
thank
once
you
again,
so much.
I thank everybody for the active participation, and then we see you tomorrow for the next lecture. Thank you.
Thank you.